this brings us to, okay, so you've got to do some operations here. You've actually got to do the Fourier transform to do this. Here is other facts. When you do the Fourier transform, the routine is called the FFT. Now, if you notice, Fourier is only spelled with one F. Right? So you know that probably one of these F's is Fourier. Since you're doing a transform, maybe that's what the T stands for. What does the other F stand for? Fast. Yeah, so first of all, aren't all things fast? So how fast you got to be that your name is fast, right? Because it's always assumed that things are fast on the computer. Fast Fourier transform. It tells you a lot right there. Not many algorithms have the name fast in them. Okay? This one does. In fact, at the end of the millennium, remember right before everything went nuts because 2000 came and all the computers crashed and the world went into a giant abyss of chaos? Remember that? Okay. Justin Bieber arrived. You guys shouldn't be embarrassed by that because I'm going to blame your generation for that guy. Okay? Seriously, that's a knock against you. Well, anyway, back in the old days, all right, the fast Fourier transform, when we were trying to work with this, people had really slow computers. And what you were looking for is ways to actually solve things very quickly. And what you found here with the fast Fourier transform is you could do a fast Fourier transform and the operation count. Remember, the operation count is everything now for us. N log n. That is magic. Okay? You can beat that, you'll win a Fields medal. Okay? This is the state of the art, as it were, or the best people have really been able to kind of do. So n log n. So when you think about solving that differential equation, n log n, first Fourier transform f, and then n log n out. So you can solve that differential equation essentially in n log n speed, right? Which is pretty amazing. Because if you did it in other ways, it actually costs you a lot more. So the fast Fourier transform becomes your kind of tool of choice if you can use it. Now, if you can use it, that's kind of the big thing. Remember that we're actually going to work on this domain now. Not negative infinity to infinity, but minus L to L. Finite size domain. And remember that our kernel are things like this. This is our kernel. That means we have periodic boundary conditions. Okay, so this is something you're going to have to think about. Is it going to make sense for your problem? Okay? No, by using it, you're assuming periodic boundary conditions.
Okay, so yeah, so your problem has to be periodic on the boundary to use.
Or does periodic make sense for that problem? So let's talk about that in a minute. So that's what we're going to talk about next, which is by using this, you're enforcing periodic boundary conditions, and you have to say, well, does that make sense? Because my problem maybe doesn't have periodic boundary conditions. However, can I still get away with this? A lot of problems that you solve on the interval negative infinity to infinity, out at infinity, this thing is 0. And over there at negative infinity, it's 0 too. So who cares if I impose periodic boundary conditions? Everything's 0 out there. So a lot of sort of infinite domain type problems, you can get away with this just fine. Doesn't care. Doesn't see the periodic boundaries. Okay? 3. So Fourier transforms were around for a while. And I made the comment. Back then, when this was invented, this was the late 60s. How fast do you think the fastest computer was? take an iPhone now, right? And back then the fast computers were in sort of giant rooms, right? And your iPhone is just so much faster than anything they had there. So they were always very conscious of operation count. So the guys who actually developed the FFT were two guys named Cooley and Tukey, okay? And okay, so late 60s, and computation back then was confined to a small, very wealthy group, usually government, that could perform computations on some machine that took up several rooms. But what they found was, here's the basic idea behind the fast Fourier transform. Before that, it cost you order n squared. And what they said is, wait a minute, let's do the following. And we're actually going to talk about this in detail later in the course. But what they said is, if I break this up into endpoints, if I'm going to solve for all the Fourier coefficients, it's going to cost you order n squared. But here's what they said. There's a way to break this problem of n points up into two problems of size n over 2. But each problem of size n over 2, I can break up into two problems of size n over 4. So I went from one problem of size n to two problems of size n over 2 to four problems of size n over 4. And if I can keep breaking it down, if I can discretize this like 2 to the n, I will solve n problems of size 1 by 1. A 1 by 1's easy to solve. Remember, every n by n problem you solve costs you order n cubed. So if I can solve a 1 by 1, that's trivial, and then I can bring it back up. That is the way the algorithm works. It breaks the problem down into half size, half size, half size, half size, all the way down to a bunch of 1 by 1s, and there's a very specific connection formula from the 1 by 1 problem back up. Okay, and we'll talk about that later. But that's also something you want to keep in mind. Now, this isn't quite as important as it used to be. It used to be, for instance, if you're going to discretize the domain and you say, I'm going to use 128 points, right? Because that's power of 2. So you'd want to use 16, 32, 64, 128, 256, 512, whatever. And if you came along and said, well, actually, I want 200 points. Used to be you paid full n squared then to do that. Okay? Now, MATLAB, not trusting you, says, or a lot of algorithms say, well, okay, fine, use your 200 points, but what we're going to do in the background, we're going to do this. Because we want to get the n log n. So even if you use 200 points, you almost get n log n speed. Okay? But generically, try to use 2 to the n if you can. Because then it doesn't get any overhead beyond that. And then the final thing is accuracy. I'm going to put this phrase here, which won't mean much. The accuracy properties of Fourier transforms are what's called oftentimes beyond all orders. So for instance, when we discretize using finite difference methods, and you say, calculate for me a second derivative, right? So if you use two neighbors, it's order delta x squared. It's algebraic, so delta x to some power. And if I want a more accurate scheme, I can get delta x to the 4 or delta x to the 6. The accuracy of this is beyond any algebraic order. It's exponentially accurate. Okay? So you're going to be able to get, for the same discretization, this will be far more accurate than you'll ever have a finite difference scheme be. Okay? So, ton of advantages. And here's your big disadvantage. You have to ask that question, can I live on a periodic domain? And I like to always say this is like having a Ferrari. You have this super sweet, fast car that just can fly, as long as it's on a track. Okay? You can't go off-road with that thing. You'll crash. Or just even a dent, and it's $100,000. Okay? All right. So that's the constraint. Yes, you have a fast car, just like Tracy Chapman does. And then you have to be on a track. So periodic. All right. Yeah?
So if you have periodic boundary conditions, or you can assume periodic boundary conditions. Is there any reason not to use fast-forwarding transform?
None. In fact, it goes back to our question. If you're not using the FFT when you can, I would argue you're doing it wrong. Okay? Because you not only get all the accuracy and all the speed, I mean, you get this combination that this is all you're looking for. How fast and how accurate can I get a solution? FFT, if you can use it, gives you the best of everything. It's almost too good to be true except for that. Okay? All right. So in fact, we're going to kind of go through some of this stuff when we start to evaluate schemes. Because part of what we're trying to learn here is also how do you do an evaluation of what scheme I should bring into a problem. And so we have to start thinking about what are the evaluation criteria we have to use for you to start thinking about that.